Well, good evening and welcome to the second annual I Heart Pluto Festival. And thanks everybody for your patience. You know, it took 25 years from concept till New Horizons flew by Pluto. So 25 minutes maybe isn't as bad as that, but we appreciate you waiting. We had some technical difficulties because of weather here in Flagstaff. My name is Kevin Schindler and I'm the historian at Lowell Observatory. And it's my pleasure to host this event this week. In fact, I'm at Lowell Observatory snowed in, and this office has some Pluto history because before my time, it was where Jim Elliott used to stay here in summers. Jim was a Pluto expert. He pioneered the study of solar system bodies by occultation when solar system body passes in front of distant stars. And it was using that technique that he and colleagues from Lowell and other places detected the atmosphere of Pluto. So it's kind of neat to be sitting in this area that has a lot of aura. This week we'll be giving talks every night, and we also have some ongoing events. Our friends Karma Sushi Bar Grill downtown has brought back their popular Pluto roll, and we also have our local ham radio group that's broadcasting from our parking lot, even right now with all the snow. And then we also have an art exhibit by the International Association of Astronomical Artists. And you can view that at our website, iheartpluto.org. And I also want to mention our gift shop at Lowell, our online gift shop. We have a lot of Pluto items, especially right now. One of these items that you can order is this book called Chasing New Horizons. And this was written by David Grinspoon and our speaker tonight, Alan Stern. Alan, if you're friends with Lowell, gosh, you don't have to be a friend of Lowell. I think if you've been paying attention to the news the last 10 years, you know Alan's name. He's a planetary scientist. He was the principal investigator for the New Horizons mission that flew by Pluto. He's twice been named one of the 100 most influential people by Time magazine. He serves on Lowell's advisory board, and he's done just about everything but go into space. But that's going to change within the next couple of years because he's the first NASA-funded commercial space crew member. So we're really pleased to have Dr. Stern here tonight. And with that, Alan, I'll turn it over to you.
Well, thank you, Kevin. And I'm glad to be here this Saturday evening and share part of the evening with all of you, talking about a topic that's near and dear to my heart. Let me share slides. And I'm going to stop my video to make sure that we have the bandwidth and make this full screen. And okay, so I'll get going now. So my topic tonight is why Pluto is a planet, the embarrassment of the IAU, and why they had it coming. And just in case you think that might be a little bit forward or pushy, here's where I got the idea for the title. There's Mike Brown, a planetary astronomer, on the right, and the cover of his book on the left, How I Killed Pluto and Why It Had It Coming. So I thought this was a fair turn of phrase. Mike has not been doing very well in recent years in convincing people that Pluto should not be a planet and that dwarf planets shouldn't be a planet. He's also not been doing very well on his search for so-called Planet 9. And I was shown this recently, this kind of tongue-in-cheek cartoon of the two of us, which I got a big kick out of. But, you know, I want to talk about the real Planet 9, Pluto, which was discovered at Lowell Observatory by Clyde in 1930. This is an image of Pluto with a little inset image of Pluto's atmosphere, both made by New Horizons in the summer of 2015, as our NASA spacecraft flew past the planet and imaged it. And here we've wrapped images of the planet onto a sphere and given it the impression that you would have if you were riding along a little bit closer flyby than New Horizons. And why don't we get started on what I really want to talk about? And let me begin that by saying that there have been two big revolutions in planetary science during the time that I have been a planetary scientist, since I got my PhD in 1989. One is the discovery that interior water oceans are common in the outer solar system, that there are many potentially habitable worlds that we never thought were habitable before. But the other, equally important and really mind-blowing discovery has been that Pluto's not an oddball. It's actually the tip of the iceberg. Beginning in the early 1990s, as we started to uncover the nature of the Kuiper Belt, this third zone in the solar system, which lies beyond not just the terrestrial planets, but also beyond the giant planets. And we discovered Pluto's cohort. We found that the Kuiper Belt is not just teeming with comets and planetesimals left over from the formation of our planetary system, but also teeming with small planets, dwarf planets like Pluto, which now outnumber the terrestrial planets and the giant planets combined, and which are expected to ultimately number by the hundreds when surveys are complete. And it's this dwarf planet revolution that we had no inkling of, even as late as the 1980s, that the population structure of the solar system would be stood on its head with more small planets than big planets. That's really been, as I said, one of the two biggest stories in terms of discovery about our solar system in the time during my career. Now, many of you know that the International Astronomical Union reacted sort of in horror to the discovery that there are lots of small planets. And in 2006, drafted a definition of planet. It states that in the solar system, a body is only a planet if it meets all three of these criteria. Number one, that it's a celestial body that is in orbit around the sun. Number two, that it has sufficient mass so that it assumes a hydrostatic equilibrium. That just means that it's big enough for gravity to round it. And three, that it's cleared the neighborhood around its orbit. Now, this definition has caused a lot of problems. And I'm going to walk through why it's so problematic, and then talk to you about a better definition hatched by planetary scientists, not by astronomers who study stars and galaxies and black holes, but by actual experts in the field. But first, let's deconstruct the problems. Let's go over the problems with the IAU planet definition, which I'll refer to as the IPD. Now, as I said, and here's a picture during their vote. We're going to talk about voting a little bit at the end of this talk and why it doesn't work in science. But one of the problems, I think really the root of the problem with the IPD, is that it was created by non-experts, by astronomers who study all those faraway things, but who are not expert in the study of planets. And they kind of botched it. To be honest, I think if a bunch of planetary scientists at a technical meeting got together and tried to define black holes or galaxies, we'd probably botch that too. But nonetheless, they got a lot of press with their definition, but it's truly flawed. But before I talk about how it's flawed, I just want to say, it's a little funny that the purpose of the IAU in creating this definition was to limit the number of planets in our solar system so that school kids wouldn't have to memorize long lists of planets. Now, I think it's a little strange that astronomers became afraid of astronomically large numbers. And throughout science, we have large numbers of lots of things. There are countless rivers on the Earth, but the geologists and the hydrologists don't limit their numbers to the 7 that you can remember. We have lots of mountains. We have lots of stars and asteroids and everything else. Really, there are no limits in astronomy or in other sciences on the number of anything except for planets. This is a little bit odd, and frankly, defining planets to limit their numbers is a complete anomaly, not just in astronomy, but in science as a whole. It's really an engineering solution to a scientific problem, which is classification. If we can't have large numbers of planets, are we going to limit ourselves to just 8 stars, 8 galaxies, 8 species, 8 rivers or mountains? How about just 8 states in the United States? That would make it easier on school children. What about 8 elements? I mean, the periodic table has, 100 and something elements these days in it. Here's the periodic table. You can see all those elements, some of which have only been recently discovered, in fact. But if the IAU were running things, they would only keep the number down to something people could remember. We'd have 8 elements, and it would stop at beryllium, and that would be the end of chemistry. This is not really scientific. It's not a very good example for the world pedagogically or for science in how to do science. Now, more seriously, as I said before, the IPD really is deeply flawed. And I want to talk about how it's flawed. And so let's start with part 1. Here's fatal flaw 1. The part 1 of the IAU definition says a celestial body, to be a planet, an IAU must be a celestial body that is in orbit around our sun, our sun. Here's a beautiful picture of exoplanets. There are thousands of them that have been discovered around other stars. By the IAU definition, none of these are planets because none of them are in orbit around the sun. So, frankly, they started off on a bad foot. Fatal flaw number 2 says, the part of the definition says that to be a planet, it's cleared the neighborhood in its orbit. I don't know anybody who knows how to define that, but more importantly, here's a beautiful rendition of all the asteroids that orbit in the inner solar system and the orbits of the planets, the terrestrial planets, Mercury, Venus, Earth, and Mars. Right? And then you can see the giant planets much farther out. But take a look at that. Does it look like the Earth has cleared its zone, or Mars, or Venus, or Mercury? They have not. In fact, they can't keep their zone cleared because new objects are constantly being fed into the population. So, in fact, by the IAU's definition, strict interpretation of the word cleared means that there are no planets that qualify in our solar system because no neighborhoods anywhere in the solar system, from Pluto down to Mercury, are fully cleared. They never are. And it's crazy to think that any planet could completely clear its zone because the solar system is so dynamic. And each of these 3 images shown here show populations all the way out to the Kuiper Belt that litter the region where all of the planets lie. And Pluto's no different than the Earth or the giant planets or Mars or Venus or Mercury in that regard. Lots of small things cross its orbit. It has not cleared its zone. Neither have the other 8. And neither have all of the little planets, the dwarf planets that we have discovered even farther out. Now, fatal flaw number 3 of the IAU's definition is that planethood turns out to not just be based on an object's attributes, what you can tell from looking at that object, but also on its location and its surroundings and the mass and age of its star. And you might wonder why that is. That's because when you write down the equations for clearing a zone, it turns out, and there's a nice little equation down here. It's the only equation I'll show this evening. To be an IAU planet, your mass has to be greater than this equation, which depends upon the mass of the star to the 1/4 power, to the distance from the star to the 9/4, roughly the square of the distance, and the age of the system. And this means, in particular, this dependence on distance means that the IAU's planet definition inherently and strongly biases against distant planets because as you go farther out, the zones get larger and larger, and the planetary orbital speeds drop according to Kepler's laws. And the end result is that farther out planets take longer and longer and longer to clear their zones. So you end up with a very funny situation where in order to know what qualifies as an IAU planet and what doesn't, you actually have to do math when it's not that hard. Now, pursuant to this third fatal flaw, here's a wonderful piece of social media about it that I saw a couple of years ago. One thing that the the equation that I just showed means is that as you go farther out, you require more and more mass to clear a given zone. And that means that if you were to translate the inner planets out to the Kuiper belt, if you moved Mercury or Mars or Venus or Earth out to the Kuiper belt, it would no longer be a planet by the IAU's definition. So if there were two Earths, for example, one orbiting where we live and another out in the Kuiper belt or farther out, even though they were identical objects, they would classify differently. And I think this is really the stake in the heart of the IAU's planet definition, is that it ends up with ambiguous definitions in which identical objects qualify differently. That's crazy. We don't say that, for example, an Arabian horse is no longer an Arabian horse when you take it somewhere else in the world and take it out of Arabia. But there's a better way. It's called the Geophysical Planet Definition, and it was created by planetary scientists, actual experts in the study of planets. And here's a little article that was in Astronomy Magazine a couple of years ago, written by myself and Kirby Runyon, another planetary scientist, about this geophysical planet definition. And I'm going to summarize its attributes and why so many planetary scientists prefer it over the IAU definition. So what is the geophysical planet definition? It's simpler. There are only two criteria. It's a celestial body that has sufficient mass so that it can assume that hydrostatic equilibrium or nearly round shape. It's a big round thing due to gravity, but with insufficient mass to undergo nuclear fusion in its interior, because if it did nuclear fusion, even though it's big and round due to gravity, we would call it a star. And all the planets of our solar system qualify by this. It has many advantages. At the top of this graphic, you can see the sun, the orange thing on the left, and all the planets of our solar system that qualify by the Geophysical Planet Definition, or GPD. And so you see the four giant planets, then the Earth, then Venus and Mars, and so forth. And in fact, if you're looking for Pluto, it's right in the middle of the pack. Oh, I'm sorry, that's Pluto, right in the middle of the pack where my cursor is. It's by no means the smallest, and it's by no means the largest. It's a pretty typical world. Now, the advantages of the GPD are, first, it's based only on a celestial object's attributes. That is, when you look at the object and measure things about it, you can tell if it's a planet or not without knowing anything about what it's next to or where it is or how it orbits. So in that regard, it's parallel to most other categorizations of objects in the universe. We can tell an asteroid by its intrinsic properties. We can tell a star by its intrinsic properties. We differentiate neutron stars from black holes, for example, by their intrinsic properties and not by what they're next to or how they orbit. Further, the GPD is agnostic to the number of planets. It doesn't care if there are a few or an uncountable number. It just puts them in a bin, and then the data is what the data is. And it doesn't limit planet categorization to only our solar system. It applies to all planetary systems around all stars. In fact, even planets that have been ejected out of orbit around a star and which now orbit in the galaxy classify as planets by the GPD, which I think is a very nice feature of it. Here are a couple of other advantages. As I said, it doesn't depend upon location, and it embraces the diversity of planetary sizes, types, and orbits. But best of all, it's simply intuitive. You don't need a lot of math. You don't need a computer. You don't need a map of the solar system. You don't need to simulate zone clearing or anything else. In fact, the GPD reproduces pretty well what I call the Star Trek test, which is on a Star Trek episode, no matter what your favorite brand of Star Trek is, when the starship shows up at a new place and they turn on the viewfinder, and you see what's there, you can tell if it's a spacecraft or an asteroid or a comet or a planet or a star or what have you, without having to do any math, without having to do any mapping of what else is around it, without having to survey an entire star system and start doing calculations. In the same way as the Star Trek test, the GPD is completely intuitive. So let's get real. There are countless stars and there are countless planets. And who cares? It's just the data. Yes, back in the quaint 20th century, we only knew of 9 planets. But as our telescopes and detectors got better, we started to discover lots of new planets in our solar system and lots of planets around other stars. And we have to give up that old 20th century notion that we could remember the names of all of them, in the same way that we can't remember the names of all the rivers of the earth or the mountains of the earth or all the asteroids or all the stars or all the species on the earth. This is big science, and there's a lot of data. And we as scientists are reductionists, and we want to have classification systems that let us sort things into bins, but we don't require memorization. That's not science. That's stamp collecting. Now, another thing that comes out of the GPD is a similarity between stars and planets. So this is a number of different stars. Some are giant stars and some are dwarf stars. In fact, here's the sun. It's that little dot there where the arrow's pointing. As large as the sun is compared to the Earth and Jupiter and the planets of our solar system, it's a tiny little star, technically classified as a dwarf star. That doesn't make it not a star. And you can see how much larger many other stars are. In fact, some are of the scale of our whole inner and part of our middle solar system. Stars span a very wide range of sizes. And now we know planets do too. There are lots of little planets, just like there are lots of dwarf stars. And there are smaller numbers of giant planets, just as there are smaller numbers of giant stars. And in the same way that both these animals, named Pluto and Jupiter, are still canines, despite the big size disparity, biologists would classify these in the same species. Even though they don't look much alike, there are deeper connections, and the same applies in classifying planets. Now, the other thing that I would like to go over is that small planets have a lot more in common with other planets than with small bodies. Here's that image of Pluto made from New Horizons images at the flyby, with asteroids that have been flown by spacecraft here in the upper right, all shown to scale with Pluto. And of course, they don't look very much alike. It's because when objects become large enough for gravity to take over and round them into spheres, different kinds of geology and geophysics takes place. And to our eye, we recognize them as planetary bodies like the Earth, and not like the shards of creation, like these small asteroids. Take a look at them. None of them look to you like what you would see, what you would think of as a planet on a Star Trek episode. Nor, by the Geophysical Planet Definition, would any of these qualify, because although they're celestial bodies in space, they're not large enough to be rounded by self-gravity. Here are the planets of our solar system, from the Earth to Pluto to many of the others. In fact, by the Geophysical Planet Definition, even the large satellites, like the Galilean satellites, or Titan or Triton, classify as planets. They're still moons. They orbit another planet, but they're large enough to be rounded by self-gravity, and they are in space, and they classify as planets as well. And just as asteroids orbit asteroids, stars orbit stars, and galaxies orbit galaxies for that matter, planets can orbit planets too, in a modern view of planetary science. Now, this GPD is not new. When the IAU took their vote in 2006, it didn't take more than about 10 days for 300 planetary scientists. Some of their names are listed here, including my own, but here you see the numbers. I was number 265 to sign on to this resolution that refused to use the the IAU's planet definition because it was recognized from day one by planetary scientists to be flawed. In fact, the resolution said, we as planetary scientists and astronomers do not agree with the IAU's definition of a planet, nor will we use it. A better definition is needed. And this is literally 10 days after the 2006 vote by the IAU at their little meeting in Prague. So let's talk a little bit about the embarrassment now with the IAU. And I want to start with the fact that it's the IAU planet definition is largely ignored. And this was shown beautifully in 2018 by planetary scientist Phil Metzger at the University of Central Florida, who found by doing an enormous literature search that the IPD definition is ignored by scientists. He could find zero, let me say that again, zero planetary science research papers out of thousands that have been published since 2006 that use the IPD. The only papers he could find that even mention the IPD were papers about the IPD. The reason that planetary scientists don't use it is because it's not useful. It produces all the screwy outcomes that we talked about 10 and 15 and 20 minutes ago, with different classifications in different star systems and different classifications at different distances and all of the other problems that I reviewed. But by contrast, Professor Metzger found hundreds of research papers that use the geophysical planet definition. So the score is hundreds to zero. The IAU planet definition is not being used. Yes, it's in textbooks, but it's not being used by the research community, which I think is a severe indictment. Now, I want to talk to you about Neil Tyson a little bit, who famously threw Pluto and the dwarf planets out of his displays at the Rose Center in New York. I have a recording, but unfortunately it doesn't play on this PowerPoint. It's a recording of Neil Tyson in 2016, and I have to break out of this, and I'm going to play it for you now. Let me just start it, and hopefully you'll be able to hear this.
If dwarf planet is a category of planet, well, I have no problem with that. If dwarf planet is a category of planet, well, I have no problem with that. If dwarf planet is a category of planet, well, I have no problem with that.
Okay, I think that's enough of Neil. Bless his heart, he's recanted. Sometimes he says he's recanted and sometimes he says he hasn't, but you heard him on tape on his own radio show, Star Talk, in an interview with me saying just what's in quotes here. If dwarf planet is a category of planet, I have no problem with that. And let's talk about one more thing. About a year and a half, almost 2 years ago, in the spring of 2019, the Philosophical Society of Washington invited me to debate Ron Eckers, who was the IAU General Secretary in 2006, to debate this very topic of planet definition. It didn't go very well for Professor Eckers. In fact, at the end of that debate, they took a little vote among the participants, both online and in the room. You can still find it online. Here's some social media pointing to it. But here's the vote. The green bar is for the IAU planet definition, and the blue bar is for the geophysical planet definition. So why did I say, beyond the embarrassment of the IAU, that they had it coming? It's pretty simple. Voting is a terrible mechanism for doing science. I don't know of any circumstance in which scientists have gotten together and voted on a scientific matter in any official capacity. We don't vote on the theory of relativity. We don't vote on genomics. We don't vote on continental drift in geophysics. We don't vote on quantum mechanics. There's no parallel. In fact, voting isn't a very good process for science. You could put 100 scientists in a room and they could vote the sky is green, but that wouldn't make it so. Voting is wonderful in democracies and for making governance decisions, but not a very good process for actual scientific classification or other matters of science. In fact, I would venture to say that this image of the IAU taking a vote among just whoever turns up to be in the room at a meeting in 2006 was the single most damaging pedagogical event in science probably in a century. Because to many people, lay people who were watching, it was easy to reach the conclusion that science is arbitrary or political, which it is not. It was easy to reach the conclusion that perhaps all other science is arbitrary and done by voting. Now, those of us who are scientifically literate know that that's not the case, but when these images went out around the world of a vote on the IAU resolution for a planet definition, it really set science back, in my view, because it gave the impression of science being political and arbitrary, when in fact we know that the way that scientific theories become paradigm is by amassing data that supports that theory and by scientists making up their mind, one scientist at a time, until we have a consensus that relativity is a better theory of gravity, for example, than Newtonian mechanics, or that quantum mechanics is a better theory of how atomic physics works than was the Bohr model of the atom of the earliest 20th century. That continental drift is a real geophysical phenomena, which is supported by data. And on and on and on across science, we never get together and vote on one another's scientific papers or discoveries, or even vote on whether we buy or don't buy a scientific presentation, whether it's a seminar or at a scientific meeting. This is why I think they had it coming, because without meaning to, the IAU created a drastic setback for science. So I hope that in the last 40 minutes or so, I've given you a look at why the IAU planet definition is so flawed, why the geophysical planet definition is so much better, why the IAU should be so embarrassed now because no one uses their definition, and why they had it coming. And I think with that, I can give it back to Kevin, and we can take questions for as long as he would like, long or short as he would like. So I will keep sharing, and I'll turn my camera back on now.
Okay, thanks so much, Alan. That's a great overview and really gets to the nuts and bolts of a lot of this discussion. And we have several questions, so let me just start throwing them at you. Here's the first one. Wouldn't hydrostatic equilibrium depend on what a planet is made out of in temperature? Wouldn't a small gob that can melt also get to hydrostatic equilibrium?
Those are great questions, and I've heard them before. In fact, hydrostatic equilibrium does depend upon a number of different factors, and the equation of state, or as the average person would say, what it's made of, is part of that. But it really is only at the margin. It's kind of a detail, a second order detail. And, a lot of things in science are complicated. We left black and white behind a long time ago in science, just like a lot of us left black and white about the world behind probably when we were teenagers, and realized there are all kinds of shades of gray. There are shades of gray at the boundary of every definition in astronomy, from the boundary between dwarf galaxies and full-blown galaxies to the boundary between stars and brown dwarfs. And yes, there's fuzziness at the very boundary of planethood, depending upon what it's made of. But that doesn't change the fact that the GPD is a far superior definition. And as to your question about wouldn't a little glob of something molten that became round then be classified as a planet, that's not the case. In fact, that little blob of whatever, whether it's metal or water or whatever that might be a liquid, it becomes round, the size of a marble, or the size of a basketball, or the size of a swimming pool, or the size of a building, it comes around for a different reason, because of a different process than hydrostatic equilibrium, due to surface tension that shapes it just like a soap bubble into a sphere. That's different physics, and only large things, hundreds of kilometers across and larger, become rounded due to self-gravity. Kevin.
Okay. Here's a question from Jeff Slifer, a family name familiar to us here at Lowell. What would it take to get the GPD adopted? Is it important for the IAU to recognize it, or is it just a question of popular adoption?
Yeah, I'm glad you asked that. Lord help us, we don't want the astronomers to try again. They've botched it up bad enough. But worse, that's not how science is done. Science isn't done by groups of people at a meeting taking votes. The way that science is done is by individual scientists coming to reach a conclusion. And I think we see from Phil Metzger's work that planetary scientists uniformly have reached that conclusion. They use the Geophysical Planet Definition. And you can't find papers in the literature that usefully use the IAU's planet definition. Now, I know that's a little frustrating because a lot of people would like to see the IAU change. That's the last thing a lot of us would like to see, because we don't want to take another vote. That's anti-scientific. And for all I know, the IAU would make it worse. It's really planetary scientists who have already decided, and they have voted with their feet in the written literature, thousands of scientific papers that ignore the IAU planet definition. The trick here is to somehow convince textbook writers that we don't need to take a vote, because they're still teaching the IAU planet definition when no one's using it. Kevin.
And that does bring up an important point about science, is that it's fluid and it's essentially a progress report. Based on the best information you have right now, this is your explanation. But as you learn more, your interpretation can completely change.
Exactly right. Although usually when we've got something right, it sticks. And so, for example, our understanding of the atom really got fixed about a century ago. And then we've been exploiting that understanding ever since. And the understanding of gravity, similarly, through the theory of relativity. And many of the things that we learn in science, they can evolve as we get a bigger data sets. We used to think there were only a couple kinds of planets in our solar system because that's all the ones that were around here. Well, the Arapaho Indians that used to live in the valley where I live, near Boulder, Colorado, probably only knew of a very small number of species that are natural to this area. But if you took those folks on a world tour to see all the diversity around the world, they would have to enlarge their view that there are many more species on the Earth because they have more data. In the same way, these discoveries of new planets in our solar system and new planets across the galaxy are showing us not just that planets come in different sizes, different orbital types, and can be around different kinds of stars than our own, but also that there are whole new kinds of planets, like pulsar planets, like hot Jupiters, like super Earths, and balsa wood planets that are not literally made of balsa wood, but have a density of puffballs, and so forth and so on, that we never imagined when our data set was just the planets that were close to home, the only ones that we could see in the 20th century.
Okay, here's another one. Do you think the dwarf planet versus planet categorization impacts the science that is done? Specifically, when we have a probe, for instance, en route to Eris, if it were considered a planet?
I think that we've gotten past that for the most part. I think that in planetary science and in places where planetary science is funded, like at NASA and the National Science Foundation or the European Space Agency or so forth, that the dwarf planets are recognized as equally valuable bodies. And, as I said during the presentation, the sun is a dwarf star doesn't make it a less valuable star to study. This terminology that we have in all the space sciences with dwarf galaxies and dwarf planets and dwarf stars and so forth and so on is just a common terminology. It's not a value judgment.
Okay. Let's see. This question is, how would we define a moon? In a system where you might have two bodies in common orbit around a star, would the planet be the one closer to the center of mass? Are moons planets now?
By the geophysical planet definition, if it's large enough to be rounded by gravity, it is a planet, whether or not it orbits another planet. In fact, even as I said earlier, whether it orbits anything at all, it could just be free floating in the galaxy. And those types of bodies have been discovered in the last 20 years through experiments called microlensing. These are escaped planets that have been ejected from their solar systems, but that doesn't make them not planets. The geophysical planet definition recognizes an object as a planet independent of its orbit, independent of its location or circumstance. It's simply what is the body. And so big satellites that are rounded by self-gravity qualify as planets. And as I said earlier, they're still moons because they orbit another planet. And so, as you were suggesting, I'm speaking to the questioner, in a system with many planets, such as Jupiter's or Saturn's, where we have a number of moons that qualify as planets, the central body is the one which is closest to the center of mass and which dominates the system. And all of the other planets, we usually call secondary planets or satellites interchangeably.
Okay, here's a question from Eleanor Service. What about Pluto's ratio of mass to the ratio of aggregate mass of objects in its orbital zone? Pluto, Sirius, and Eris are less than 1 for this ratio, while Earth is 1.7 million.
Yeah, so you're right. In for example, the circumstance of the Earth, all those teeming numbers of near-Earth asteroids that create all the hazards that you read about and that created events like Tunguska a little over a century ago, or the KT boundary and many other impacts on the Earth. All those bodies sum up to a much smaller mass than the mass of the Earth. In the case of the Kuiper Belt, Pluto's mass is much less than the mass of the Kuiper Belt. But that's really just an issue of location. It's just an issue of circumstance. And what planetary scientists, voting with their feet, as I said, in hundreds of published scientific papers, identify as planets are bodies that reach this state of roundedness due to gravity called hydrostatic equilibrium, independent of their circumstance. And so throughout the planetary literature, Pluto is called a planet, the Earth is called a planet, Titan that orbits around Saturn is called a planet in the literature and in scientific talks, and so is Io, and so is Ganymede, and so is Callisto, and so is Triton, and so is Eris, and so forth and so on. Because where you find it doesn't affect what it is. It simply speaks to where it is and what else might be around it. And there are lots of circumstances across the galaxy that put planets in different populations. The same is true in our solar system. It's no different.
Okay. Alan, before the next question, could you turn off your screen share?
Sure. Let's do that.
And then here's a different, coming from a different angle. Do you have any advice for a current astrophysics student?
I give you two pieces of advice. The first would be to study hard and really excel, but even more importantly, find the part of astrophysics that you love best. If you do what you love, you're more likely to excel at it. And so the types of homework problems or research projects or laboratory projects that you find make you most excited and are the most fun in spending the time are most likely pointing you in the direction that you should go for where you want to specialize a little bit later when you become a graduate student.
Okay, we'll get back to some Pluto stuff here. Why do you think the IAU hasn't officially named more dwarf planets into the dwarf planet category?
Lord knows, ask them. We sure have a lot of dwarf planets that are not categorized as dwarf planets by the IAU, but which are referred to that way in the scientific literature. And you see, that's the beautiful thing about science. It happens one scientist at a time. And we don't need an authority to pass a resolution in order to use vernacular and to develop vernacular and to hone our terms. This happens organically in all the sciences, not just planetary science, not just astronomy, but also in biology, zoology, geology, geophysics, and on down the list across all the sciences.
Here's a question from Peter Jeddick. Do you have an argument that includes Pluto as a planet, but not any of the other dwarf planets and moons? That's what most Pluto huggers are looking for.
Well, I don't know very many scientists that, in fact, I don't know any scientists that think of planet definition that way. And I count myself among Pluto huggers, or I wouldn't have spent so much time over the last 20 years getting New Horizons built and flown across the solar system and analyzing data from it. But I wouldn't look at the world that way for a minute. And maybe there are some lay people who are that way, but I don't know any serious scientists who would interpret things that way. And I don't know any serious planetary scientists who would call Pluto a planet and not, for example, Ceres. Because very clearly Ceres is a planet by dint of being an object in space that's become rounded by self-gravity.
Okay. And if you're good to keep going, we've got some more here. Okay. Other than Pluto, what would you say is the most interesting dwarf planet that people are ignoring because of its status?
Well, scientists don't ignore dwarf planets because of their status. And in fact, right now, the Planetary Decadal Survey is looking at possible missions to new dwarf planets, even to go back to Pluto with an orbiter. Of course, they're very tough. It's a very tough competition because there's a certain amount of money chasing after. Many more missions are chasing after that money than we can afford. So in a typical Planetary Decadal Survey, something like 1 in 100 ideas actually reaches fruition, the way New Horizons did, for example. But among the dwarf planets of our solar system, there's a lot of interest in going back to Ceres after the Dawn mission with not just an orbiter this time, but a lander to actually get down on its surface to study its geophysics and its geochemistry and the possibility that it's actually a habitable abode in its interior. And there's lots of interest in going to other ocean worlds. These are worlds that are planets orbiting other orbiting other planets in our solar system, such as Triton, such as Titan, such as Europa, such as Enceladus, such as Pluto for that matter. We're turning up these oceans very often. And we already have one mission that's going to Europa to study it in detail called Europa Clipper. We have a mission now that's going to Titan to actually land on its surface and then fly from place to place around that surface. That's called Dragonfly. But missions to Enceladus and Triton, which orbits Neptune, and the lone dwarf planets of the Kuiper Belt are of very high scientific interest. Personally, I would like to see a mission to Eris and a mission to Haumea, but highest on my list is a mission to the Neptune system, to put an orbiter there to study an ice giant planet for the first time, its rings, its magnetosphere, its satellites, and its dwarf planet Triton, which in fact used to orbit in the Kuiper Belt, but was snared into orbit around Neptune to become a satellite planet of Neptune. I think if I were on the Decadal, I would be arguing for that mission because in a single swoop, that spacecraft could address the largest number of game-changing scientific questions.
Related to that, can you talk about the next potential mission to Pluto?
Yeah, the next mission to Pluto should be an orbiter. And there have now been 2 studies, one that I led, funded by my research institute, the Southwest Research Institute, which we funded in 2017 and 18, which showed that this kind of mission is feasible with current day technology, that it's affordable, and most interestingly, that after you orbit Pluto for a few years, that you can use gravity assists from the large moon and planet Charon to get out of orbit around Pluto and go back into the Kuiper Belt and do more exploring of other worlds. Following the study that we did and the papers that we published, NASA funded an even more involved, more detailed study of a Pluto orbiter. Dr. Carly Howitt, also of the Southwest Research Institute, was the principal investigator of that study, which reported to the Decadal Survey. And also found that the mission is affordable, that mission is feasible with current day technology. But they found, as we did, that that mission takes a long time, longer than New Horizons, because our job was to fly across the solar system fast on New Horizons and do a fast flyby of Pluto. But to get into orbit, you have to slow down and stop. And that braking process adds many years to the transit to Pluto, because you can't just go super fast and stop at the end. You have to brake over a number of years in order to make it feasible. And that's probably the biggest single impediment to getting a Pluto orbiter, is that the timescale to do the mission is so long. It would probably take about a decade to fund it and build it. And then it would take about 20 years to fly to Pluto. So that's 30 years from now before it would get into orbit. Whereas, for example, a Neptune orbiter that could study Triton, a dwarf planet, in addition to all the other wonderful things in the Neptune system, could get there in a much shorter period of time, because Neptune, being a very large planet, is a place where we can use a reverse gravity assist to break into orbit and minimize the amount of braking that we have to do by propulsive means. The same way that Galileo and Cassini got into orbit around Jupiter and Saturn, respectively. So we could do a Neptune orbiter with a flight time that's about 10 years, maybe a little longer, but not 20 years. And I think it's just human nature that those long time scales for a Pluto orbiter work against getting that mission funded, because there's so many other rich scientific missions like the Neptune orbiter that we can do for the same price and more quickly, and make a return and make scientific discoveries and advances more quickly. But we'll see what the Decadal has to say. I wouldn't mind seeing a Pluto orbiter at all. And if it's going to enter orbit in the 50s, then I'm just going to call that a stretch goal and try to stay as healthy as possible.
And I'll point out that we have a special reason to look forward to that here at Lowell, besides all the great science. And that's the time capsule that Alan Yu instigated, that contains, 100 plus items of Pluto memorabilia and science papers and such that we have buried, as it were, inside of the Pluto Discovery Telescope Dome, not to be open until that orbiter gets to Pluto. So for those watching, maybe you or your kids or grandkids, when that orbiter happens, come back to Lowell and we'll open that time capsule and see what's in it.
I want to be there.
The deal. Okay, let's see. Do you think the IAU was envious of Clyde's young age, or that he was American?
I don't think that really came into play. I know for a fact, because so many people who were there reported it, that the primary advocate of what became the IAU's planet definition was Brian Marsden. And Brian and Clyde had a very public spat from the 1950s to the 1980s. And multiple people had been at meetings where Marsden had said very disparaging things about Tombaugh, and that he wanted to erase his legacy. And after Tombaugh died, Marsden was successful in having the IAU vote in Prague in 2006. And I think that had more to do with it really than what the question's about. But it's also true that people who were there in Prague, I was not. I was actually putting my first kid in college that very week, and thought that family was a little more important than work at something so momentous as your first kid going to college. But people who were there said that there was an anti-American sentiment. And I think that's just a shame if that was the case. Really, politics shouldn't enter science. But at that time, in the years following 9/11, when the United States was fighting a lot of wars that were controversial, people in other countries had strong opinions, and some of those are scientists, and some of those were apparently in Prague and that apparently colored some people's decisions. I think that's a shame, but we can't do anything about it now.
Okay, we have time for just a few more. Here's a question from our friend Jeff Gagne, who's going to be participating in the iHeart Pluto Festival tomorrow night. His question, with so many exoplanets confirmed, do you think many other solar systems are like ours with several zones of planetary bodies?
Jeff, that's an excellent question. And we really don't know the answer yet. In most systems, we've only found 1 or 2 or 3 planets when we found planets. We have found that planets are very common, so common that they're around virtually every star that we have the ability to study. But we really haven't been able to take a complete census and map out the geography of these other solar systems, except in rare cases like TRAPPIST, for example, some of the TRAPPIST systems. So that's really a task for the new planet finding satellites and ground-based facilities in the 20s and the 30s. And I think that we'll live to see that geography painted out and to see just where our solar system falls in terms of being typical or atypical in a mix of interterrestrial planets and then outer giant planets, followed by even farther out dwarf planets. We'll just have to see, and we'll have to see what the data tells us. But I'm really looking forward to finding out the answer to your question. Like a lot of people who work on exoplanets and work on our planetary system, that's a very important question, and we're on the verge of starting to be able to determine the answer to it. So stay tuned.
Here's a question from Stephanie Van Bell, whose husband is an astronomer here at Lowell and was at the IAU vote, and I will point out voted for planethood. She says, given its flaws, where did the definition dwarf planet come from?
To the best of my knowledge, I coined the term. I wrote a paper in 1990 that was published in planetary science journal Eckers in 1991, in which I put together some mathematical models of forensic clues in our solar system that led to the conclusion. At that time, the Kuiper Belt had not been discovered. And at that time, Pluto was viewed as sort of an oddball, not the tip of the iceberg of so many similar worlds in the outer solar system. And that paper, which used the probability that the Pluto-Charon mutual impact that created the binary, the probability of Neptune capturing Triton that we've talked about, and the probability that Uranus would be tilted on its side by an impact with a large planet-sized body, all pointed as forensic evidence to the fact that there should be of order 1,000 Plutos in our solar system. And I wanted a term for what those objects are. And in the first 2 paragraphs of that paper, I coined the term dwarf planet to mean these small planets in analogy to small stars like the sun. And spoke, and in the paper, I basically gave the Geophysical Planet Definition without giving it a name as the criteria for planethood, and suggested that we call the small ones dwarf planets in analogy to giant stars and dwarf stars. So I'm told that I coined that term. There may have been some earlier usage that I'm not aware of, but that's the way that I understand the term was born. And you can find that paper online through Google Scholar under my name, 1991, in the journal Eckers.
Okay, last 2 questions. The first one, I think we'll end with that one. So where is New Horizons headed now, and will it overtake Voyager?
New Horizons is headed out of the galaxy, but it's going to still be in the Kuiper Belt for most of the 2020s. And as we fly through the Kuiper Belt, we are making studies of dozens of Kuiper Belt objects using our telescopes and cameras. We're now north of about 30 Kuiper Belt objects or dwarf planets that have been studied by New Horizons. Pluto and Arrokoth, of course, have been close flybys. All the others studied in the distance to determine things about their surface properties, to determine things about the number of satellites they have, to learn about their shapes, for example. The team, meanwhile, is using large telescopes, primarily the Japanese Subaru telescope that has the best wide field camera, to look for new flyby targets. With the amount of remaining fuel, the odds that we will find one that we can reach with that small amount of fuel in the tank are small. But that doesn't mean we're not going to look, because the value of another flyby is so high. So every summer, when the direction that New Horizons is traveling in the constellation Sagittarius is centered in the night sky, we use Subaru. This past year, we started that search and found 100 Kuiper Belt objects. Not quite, but almost exactly 100 Kuiper Belt objects, many of which we're already studying with New Horizons. This summer, we will look again, and next summer, we will look again. And, you know, it took 4 years to find Arrokoth, then called MU69, for that first flyby. And all of us on the team are hoping that we can find a flyby target while we're looking at all these other Kuiper Belt objects in the distance. So stay tuned. Every summer we'll report our results. And thank goodness for the Subaru telescope and its amazing camera system called the Hyper Supreme Cam, because nothing else in the world can touch it as a machine for looking for Kuiper Belt objects in the direction of our flight.
Okay, last question. What's your favorite science fiction movie or show?
Oh, that's a tough one. There's so many. I don't mean to be coy or frustrating, but I don't think it's a fair question. I don't think I can pick a favorite. There's so many different genres, and there's so many different, if you ask me for a top 10, I could do that, put 10 in a bag. But to pick my top one, I'm not going to do that. It's too hard.
Was there one when you were growing up that really, got you interested in space?
I liked a lot of movies when I was a kid, and I watched a lot of science fiction. And some of them were just more or less horror movies, and some of them were kind of goofy, like Robinson Crusoe on Mars, and some of them were kind of about the time. There was a movie called Maroon, for example, which I recently watched again, and after all these years, it didn't stand up very well. But the one movie that really stood out from that time that I think is still an amazing movie and which impressed me as a little bitty boy interested in space was 2001, A Space Odyssey. And I'd put that in my top 10 any day.
Okay, well, with that, we'll end our program for tonight. Thanks, everybody, for joining us and your patience and as we overcame technical issues. Thank you, Dr. Stern, for your always entertaining and educational talks with us. I'd like to thank our technical team, Daniel Adams, Heather Craig, and Jeff Hull, who came over in the snow from his home to get our system going. It's been a great first night. Tomorrow night, we have 2 programs. First, we'll talk about Clyde Tombaugh, who he was. We'll have Clyde's son, Eldon Tombaugh, Dave Eicher, editor-in-chief of Astronomy Magazine, and Astronomy William Sheehan. And then we'll also have Jeff Gagne here to talk about kids and how they can explore planets also. So thanks for joining us tonight, and we'll see you tomorrow.
Thanks for having me. It was a ball. See you.